Okay, so let's get started. Okay, so I guess most of you have submitted your homework. What is the situation? So how is the homework coming along? That was my question. Yeah. Okay. I see the comments. So I think this is a I'm sure it'll be a learning process for you. So clearly there were problems that were relatively easy, and there were problems that required you to think for some time. And of course, the learning experience is that when you look back at the end of the semester, I bet you will say, I can't believe that I said this was a hard homework. Okay, so hopefully that's where we will get by the end of the semester. So I will put out the next homework by tomorrow. Okay, and it'll be due maybe in another 10 days or something like that. Okay, because we need to be sort of whatever we learn in the classroom, we need to try it out on our own in order to really understand the material. So let's get started. If there are any questions about what we covered in the last lecture, you can go ahead and ask. Otherwise, we'll just continue from where we left off. So again, can more of you turn on your camera so that I have, the class is 60 people, but it looks like there are only 9 people that have turned on the camera, and that's not a good situation, right? I mean, at least half of you can turn on the camera on any given day. And it definitely helps me, and it helps, it'll indirectly help you. Okay, good. So last lecture, we ended with the discussion of power set. And in particular, we were talking about the size of we were talking about the size of the so we're talking about the size of the power set. And we will revisit this question again after covering some more material, because there is a more systematic way of thinking about sizes of sets and sizes of power set and so on, and we'll get back to that at that point. Okay. So so let's define a different operation called product. Okay. So the Cartesian product of two sets is defined like this, right? So you basically take one element from the first set and another element from the second set, and you construct this pair. Okay, sometimes this is called an ordered pair to denote the fact that in this pair, the order matters. right? So this differs from a set where the order is not relevant, okay? And in a set, the order is not relevant, and you cannot have the same element occurring multiple times. But in a tuple, you can have the same element appearing multiple times. So for instance, A comma A is a perfectly good pair, okay? And in fact, if you take two example sets here and try to compute the Cartesian product from this definition, right, then this is what you will get, right? So basically it says take any element from the first set, right? And then it says take any element from the second set and you put them together in a pair. That's one of the elements of this new set, right? So we are defining a new set called the product set from two other sets. And this, using the set builder notation, we are defining exactly what is the content of the set, right? Or what are the elements of the set. And so basically the way to interpret this set builder notation, which we have seen several times before, but again, let me remind you. So the way to interpret this is that any anything that satisfies, has this form and satisfies this condition should be included in the set, right? So it's not some of them, it's going to include all of the elements that satisfy the definition, okay? So therefore, in this case, we are going to take every combination of an element from A and an element from B, and that's how we are going to construct this. So we have a mindless way of doing this. So we pick a first element of A, and then we pair it with each of the elements of B. Okay, so we get 1A, 1E, 1I, 1O, and 1U. And then we pick the second element of A and pair it with each of the elements of B. And then we pick a third element of A and then pair it with each of the elements of B, and so on. Okay, and at this point, we are done because we have gone through all possible combinations, right? So can you tell what is the size of A cross B? Well, in general. So can you tell me A cross B in terms of the sizes of A and B? Yeah, someone, okay, let me.
The size of A cross B would be the size of A times the size of B.
Right, so this is, of course, this is integer multiplication, but this is set product. So we are using the same symbol to mean different things, but hopefully we understand the context. Okay, so because we are taking every element from the first set, pairing it up with every element from the second set, therefore the number of such pairs we can create is simply the product, right? So so that's okay. So there is not an alert pair, it's just a pair, right? Ordered pair. And just like you can have a two-way product, you can also have a three-way product. Like, if you say take a set X, multiply it with Y, multiply it with Z, then that will consist of triples of the form X, Y, Z, where X belongs to X, Y belongs to Y, and Z belongs to Z, right? So the Cartesian product is not limited to just two sets. It can be applied to any number of sets, and it basically operates the same way. You pick one element from each set and then put it together into what is called a tuple, okay? So where does tuple come from? Well, once we go beyond triple, we tend to say quadruple, quintuple, sextuple, and so on, right? So therefore, tuple is sort of the generic way to refer to this thing that that can be applied regardless of the number of elements in there. So you can have an n tuple which has n components. Okay, and once again, the size of you know an n-ary product is going to be calculated the same way, where you basically take the size of each of the sets involved, and you take the product of all of those sizes, and that's going to give you the total size of the Cartesian product. Okay, and we are going to use just as in the case of integers, right? So a times a times a. If you do this multiplication n times, then we refer to that as a to the power n, and we are going to do the same thing with Cartesian product. So we will say for a set a to the power n simply denotes a Cartesian product of a with itself taken many times, taken n times, right? So any questions so far? Okay, very good. So so I'm going to so that brings us to the conclusion of this unit on sets. So let's okay, now I need to so to summarize what we talked about, we defined our so we refreshed ourselves on the definition of sets. We tried to get familiar with the set builder notation for compactly and precisely saying what is in a set. We defined all of the standard set operators using the set builder notation. We defined the meaning of each of these set operators, such as subset, union, intersection, difference, and so on. And we quickly considered, briefly went over the properties of set operators such as commutativity, associativity, distributivity, and so on. We talked about how one thinks about equality of sets, right? So the one way to show that two sets are equal is by saying that every element of set A is also an element of set B. And then you also have to prove the other way, which is that every element of set B is also a element of set A, right? So either you do that, or you have some way of showing that A is a subset of B and B is a subset of A. When you prove both of those, that means A and B are equal. Okay. So we define the concept of a universal set, and based on that, the notion of a set complement and the De Morgan's law for complementing a union, so that it becomes the intersection of the complements and vice versa. Then we define power sets and a Cartesian product and tuples. So these are some very basic set operations that we need in order to talk about the next unit, which is about functions, relations, and cardinality. So I'm going to take the time to sort of